The big picture. In the previous section, I explained that creating tables falls under the Data Definition Language or DDL commands in SQL. You also learned how to create simple tables. Now in this chapter, we'll take things further. You'll dive into advanced concepts of table creation, gaining in-depth knowledge about table constraints and how to insert, update, and delete data in tables. So, let's jump right in. Designing and creating tables. Previously, we discussed the basics of designing simple tables with primary keys and columns for data storage. In this section, we'll cover creating tables suited for advanced relational models and live projects. In relational models, tables are linked through primary and foreign key relationships based on column values. Some columns allow null values, while others do not. The rules governing the types of values a table can hold are known as table constraints. When designing tables, these relationships and constraints need to be defined early, even before writing SQL statements. This information is gathered during the initial planning and design phases, ensuring the database structure aligns with the needs of the project. Steps in creating relational tables. The typical process of creating relational tables includes 1. Requirements gathering and conceptual design. 2. Data modeling and logical design. 3. Identifying attributes and data types. 4. Identifying key attributes and constraints. 5. Physical database design. 6th. SQL development and table creation. 7. Testing and validation. 8. Optimization and performance tuning. 9. Documentation and maintenance. Let me explain each of these steps to you in detail. Step 1. Requirements gathering and conceptual design. This foundational step involves business analysts gathering requirements from stakeholders. They study business processes, collect sample data, and understand data volume and frequency. This information is documented and handed over to data architects. Data architects and database designers then create a conceptual model based on stakeholder requirements, identifying entities and their relationships. This model is visualized in ER diagrams that map out entities and their connections. They then apply normalization principles to ensure data integrity, ultimately providing a blueprint for the database's logical and physical design. Step 2. Data modeling and logical design. The data modeling and logical design phase involves refining and enhancing the conceptual model, transforming it into a structured, logical model. During this phase, data architects fine-tune ER diagrams by clarifying entities, defining relationships, and translating business rules into specific constraints. The result is a comprehensive logical diagram that provides clear guidance on data organization, relationships, and constraints within the database. Step 3. Identifying attributes and data types. In this phase, attributes are defined for each entity, and data types are assigned based on the specific needs of each attribute. For example, integer, float, varchar, and date. The size and precision of each data type are also established here, typically by database developers. For instance, suppose you identify student as an entity. Potential attributes for this entity might include student ID, student name, student address, student age. Similarly, for the entity courses, attributes could include course ID, course name, course creation date, course description. The list grows as the model expands, with more entities and attributes added as needed. Step 4. Table constraints. Once the key attributes are set, defining constraints is essential for maintaining data integrity. Constraints depend on business rules and the type of data loaded into tables. Types of constraints. 1. Not null constraint. Ensures a column cannot store null values, supporting data integrity. 2. Unique constraint. Prevents duplicate values within a column. 3. Primary key constraint. Ensures each record is unique and non-null, combining properties of not null and unique. 4. Foreign key constraint. Establishes relationships between tables, crucial in relational databases. 5. Check constraint. Validates data based on conditions and rejects non-matching values. 6th default constraint. Assigns a predefined value to a column if no specific value is provided. Physical database design. Once logical models are completed, database administrators manage physical database design. This includes decisions on storage, indexing strategies, and partitioning to improve efficiency and data management. SQL development and table creation. This is the actual implementation phase where SQL developers build the database according to specified requirements. SQL statements create tables, enforce constraints, and define indexes, readying the database for data loading. Tips for designing tables. To ensure consistent, professional quality tables, consider these best practices. Choose consistent naming conventions: camel case, Pascal case, snake case, uppercase, flat case, kebab case. Pick one style and use it for all database objects to maintain uniformity. Avoid spelling errors. Ensure names are spelled correctly to avoid confusion and errors when working with tables. Adding comments in SQL statements. Comments make your SQL code more readable, especially for complex queries. Use double dash for single-line comments. And for multi-line comments, you can do this using the /* and */ symbols. Everything in between will be ignored by the SQL engine and treated as a comment. This is especially useful when you want to describe complex logic or temporarily disable a block of code without deleting it. Here's an example for a single-line comment in SQL. You use 2 dashes to add a single-line comment. Everything after the double dash on that line is ignored by the SQL engine. Here's an example of a multi-line comment in SQL. By following these best practices, you ensure your tables are easy to use, maintain, and work on collaboratively. Adding aliases. In SQL, an alias is a temporary name for a column or table. Assigning an alias doesn't change the original name permanently. It simply gives the column or table a temporary name in your query. Here's how to assign an alias to a column. Here's an example to explain how to assign alias to a column. Populating data in tables using insert. After creating tables, it's essential to populate them with relevant data. In addition to simple data entry, there are other techniques for inserting data, updating incorrect records, and deleting irrelevant ones. Different ways to populate data in a table. Entering all values in one go. Input all values for each column in a single insert. 2. Entering partial values. Enter values for only selected columns. 3. Importing data from other tables. Use insert into to bring in data from another table. 4. Copying data to another table. Copy records from one table to a different table. Let me explain each of these to you in detail. Entering all values in one go. Use this syntax to insert a complete record in every column. Let's apply this syntax to our table called customers. Here's the insert statement that will insert a new customer by providing values for all columns. Customer ID, first name, last name, customer address, contact, email, and order ID. Entering partial values. If a table allows null or default values for some columns, you can insert values only in selected columns. This is called partial insertion. For example, let's take the same customers table we used earlier. It has columns like customer ID, first name, last name, customer address, contact, email, order ID. Now let's say the order ID column has a default value, maybe 0 or null, and we don't want to specify it during insertion. Here's how we insert only selected values. Importing data from other tables. If you want to import data from another table, you can use the insert into statement with a select query. Here's the syntax for insert into statement. Here's an example to understand this. If you have an existing employee table and you want to import its data into a new table, employee new, with the same structure, here's the SQL statement to do this. This statement transfers all data from employee table to employee new table in seconds. Copying data from one table to another. You can copy data from one table to another using the select into statement. Unlike insert into, select into automatically creates the target table with the same structure and metadata as the source table, saving you from creating it manually. Here's the syntax, where asterisk signifies that all rows and columns from source table are copied into target table. If you only want to copy specific columns, list them instead of using asterisk. For example, in order to copy only specific columns from the employee table, use this SQL statement. Key difference between insert into and select into. Insert into requires the target table to exist before data transfer. Select into creates the target table at runtime, eliminating the need for pre-creation, testing, and validation. After completing table creation and data loading, the next phase is testing and validation. In this phase, testers and quality assurance engineers check data quality, integrity, performance, and functionality. They insert test data, validate the database design, and ensure all constraints and business rules are enforced correctly. Optimization and performance tuning. SQL developers and database administrators collaborate to monitor and improve query performance and database efficiency. This ongoing process of analysis and performance tuning is essential for a well-functioning database and requires a solid grasp of SQL. Even after a database is developed, it remains valuable for data analysis, machine learning, and building data-driven applications. Documentation and maintenance. Once the database is up and running, SQL developers and DBAs take on the critical task of documenting the entire structure and logic behind it. This includes explaining table purposes, relationships, constraints, and any business logic implemented using SQL. Clear documentation ensures that anyone working with the database, now or in the future, can easily understand and manage it. Maintenance, on the other hand, involves regularly updating the database to reflect changing business needs, applying performance improvements, and ensuring everything runs smoothly. It's a continuous effort that keeps the database relevant, secure, and optimized over time. By mastering this phase, you're not just building databases, you're making them sustainable and scalable. Each of these areas utilizes SQL functionalities at various stages. With all this knowledge, you're now prepared to dive even deeper into SQL. That's all for today. See you in the next one.